All right. So nothing in particular I would like to announce, nothing new, but I just want to remind you that your lab number 1 has been released. I cannot emphasize enough. That's your very first lab. You should definitely try to get familiar with the rodent as much as possible. You will definitely need it for all the subsequent assessment. All right? That's something you want to make sure. Do it, and at any point you might get stuck, let me know. Right? Earlier, the better. And let's now do some very quick recap about what we said last time. What we said last time was basically about propositional logic, right? Let me just do a very quick highlights about what we spoke about. So we started with the truth table of the logical operator, conjunction and disjunction. And we spoke about they are not exactly the same as the AND operator and the OR operator because there is the so-called short circuit evaluation effects that's really happening in the runtime. So if I do ask you at some written test or exam to explain the difference, you should really know how. Right? We had a very thorough discussion last time. That's the first point. And then we talk about implication. Right? Of course, you should really know the corresponding truth table. But just in case you forgot about how the truth table should really look like, you can think about the analogy I tried to make for you. But you can change the promise term and obligation to anything you like. Right? Just make sure you understand the truth table. Especially for these cases where the premises are simply false, the implication will just be trivially true. We're going to see cases where the proof can just be discharged quite easily because of this, but sometimes may not be so obvious. Okay? Just remember that. And we talk about different ways to actually expressing P implies Q. So make sure you understand every one of them. Right? Of course, they all boil down into P implies Q. But in English, you got 1, 2, 3, 4, 5. 5 different ways of saying it. You should know every one of them. All right? And we also talk about inverse, converse, contrapositive of implication. Right? I also gave you some exercise over here. Right? Just make sure you complete it. And we talk about propositional axioms and theorems as well. You want to review them, and we definitely need them at some point later. All right, and we ended our last time, our last class with the predicate logic over here about quantifiers. We got universal and we got existential. And I assume you already know about the syntax, which I tried to explain to you last time, right? Just make sure you review it. But today, I want to maybe talk about the universal and existential quantifiers. I want to make a little bit connection to programming. That may be something you had to deal with before, but you didn't realize you were actually talking about these two. Logical quantification. I'll get there. Okay? All right, guys, any question from last time you want me to address more? We okay? Awesome. So today, I will come back to this again, but I will talk about from a slightly different angle of the quantifiers. I'll get there. Let's go over a little bit more slides. So today, the plan will be, I definitely want to finish predicate logic, and at least I'm hoping to get to some topics about sets. Next week, we have to get into deep water about relations and functions. Those are the more demanding topics that you really want to pay attention to. So we'll start you fresh next week about functions and relations. And you definitely need all of them for your lab number 2 and also the assessment. Okay, predicate logic. You can think of it, it's more like an extension to propositional logic by adding the so-called universe of disclosure. Let's take a look. So a predicate is either a universal or existential. You can already see which operator you can use for each one of them. It's a statement about objects in some universe of disclosure. So this will be the kind of the term you will see a lot in standard textbook. So let me highlight very quickly. If you look at the syntax of both the universal and existential quantification over here, you can think about the range that we specify here is the universe of disclosure that's being mentioned. And the direct follow-up question would be, what if this universe of disclosure is empty? Right? What if this universe of disclosure is empty? I.e., the range expression here simply evaluate to false for any possible value. For any possible value. In this case, we're just talking about I. So, but in general, you may just have a list of variables. Right? So that's really something you want to think about. Let me draw the connection to programming right away. Right? Maybe back in your first year Java course, or maybe at least the second year Java course, when you spoke about, let's say, recursion, right? I wouldn't really get to the recursion, like a recursive method definition. It's not really the scope of this course, but I want to mention the following. Let's say here, I want you to define the Java method. Let's say I have a Boolean method. You know what? Let me change to blue. Let's say I have a Boolean method over here. And here it's called all positive. And then I have some integer array. Right? And of course, you might define some code over here. Let me give you another one, and we'll compare them. Sum positive. Integer array, and also A. You can think about universe of disclosure is being represented by integer array over here, right? It's a collection of values that we're considering for the input. Let's make that connection first. And for both of them, if you want to define the methods, let's say recursively, you definitely have to talk about base cases. Agree? Let me write down some skeleton here. You would say something like, if a.length equals 0, then you're going to do something over here. I'll leave that blank just for now. And also, if a.length over here equals 0, and you got to put something over here, right? Let me just highlight these two over here. And we're going to fill it out properly, okay? And before I ask you to give me an answer, let's just double check. This method here, it will return true if all the numbers in the input array are positive. In this method over here, it's going to return true if there is some number, at least one number in the input array that's positive. Otherwise, false. Okay? Are we clear about what these two methods should do? Okay? So these two methods are very typical of checking the so-called universal versus existential property. Okay, I'll write it down. Think about this one over here, all positive. This one here. Sometimes the method name may not indicate all versus some, but you have to be able to judge, right? So this one here is really checking some universal property. Versus, for this one over here, is really checking there exists at least one number in the input array that's positive. So this is checking the so-called existential property. You probably know the concept already, but you never knew. That's a formal term, right? Okay. Before I justify what the correct answer should be, can anybody tell me, in these two base cases, what should be returned? Just let me make it a little bit easier for you to refer to. Let's say this is number 1, this is number 2. Yes, how about just number 1?
So, I'm guessing number 1 is return true.
Return true? Okay, why?
Well, because,
So let me put it a little bit more precise, the question.
okay.
I agree with you, it should be returned true. Okay, let me write it down. Correct answer should be returned true, but we need to justify this.
So basically, before all I implies that every value inputted has to be positive.
Mm-hmm.
The moment we encounter something negative, then it becomes false. But with an empty array, you're not encountering any negative value there. So,
I like your justification. That's exactly right. Okay, so guys, for this one here, let me rephrase that a little bit. The idea would be you got to return true for this. So why are we saying in the empty array, all the elements there are positive? is simply because you cannot find any witness to prove otherwise. That's the intuitive answer. Let me write it down. Because return true because no witness in empty array can prove otherwise, which means showing that some number is actually not positive, right? That's intuitive answer. That's what I usually tell my first year student or second year. But now, let's now draw the connection to this guy over here, all right? This is really checking this. You guys are in the third year. So in this course, you have to somehow draw a connection between programming, which is what you did before, and also logic, which you did in another course. But in this single course, we want to synthesize the two, okay? So now, how do we justify this logically? If the array is empty, that means there's no such elements, it will be in this range. Agree? Just empty, right? For empty array, you can think about R over here for empty, let's say, array. Ri is simply false always. Because you simply cannot find any elements which is going to satisfy this range so that it's included in the universe of disclosure. Right? That's how you think about it. False always. And based on this, remember one of the propositional axioms we said before. Right? So if you got false implies anything, because we know this is already false, then it will always be true. All right? That's how we got this answer. Are we okay so far? Right? Quite a bit of stories being told here. You want to know, number one, let me recap, and we'll do the same thing for existential. You want to recall what you did earlier in the programming course. And whenever you're checking that, all the elements in a collection doesn't need to be array, can be anything, as long as it's a collection, universe of disclosure. If all elements in the array is actually positive, you're going to return true. In that case, the base case would be, what if the collection is empty? In that case, you cannot find any witness to prove violation. So that's why it got to be true. That's the intuitive answer. But now, for the logical answer, because you know this is an implication for universal. In that case, if the antecedent is already false, the overall implication is true, trivially. It's called the zero of implication. Okay? Hopefully that's clear for everybody. And we do the similar arguments. Yes, question? Yes. So here, think about the empty array. Think about there is no element that would be included in the empty array. Agree? If there's no element that can be included in the empty array, that means all possible I, they wouldn't satisfy the range to be included in the array. That's how we draw the connection. Think about this one here, if this range expression over here. If that evaluates to true for certain I value, that means the universe of disclosure is not empty. But if all possible value I will simply evaluate to true for this range expression, that means the universe of disclosure is simply empty. There's nothing for you to consider. In that case, you cannot find anything that can prove violation. So the property got to be true for all members, even though they don't really exist. Okay, that's kind of the logic here. Let's now talk about second one. Similar idea. What should this be, guys? Should it be return true or, well, I'm pretty sure you know the answer. How about and then? False, right? Okay, good. Wouldn't be return true, right? Good, let's see. And we're going to argue in a very similar way. Let's write it down. So this one here is going to be return false. For existential, basically, if you want to prove certain existential property, you want to find a concrete witness to really prove its existence for the property, right? In this case, in the base case where if the universe of disclosure simply got empty, that means there's no way for you to find a witness of satisfaction. So there's no way for you to prove the property, so it's going to be false. That's the intuitive answer. So here, let me write it down. And return false because no witness in empty array can prove this property, right? I'm just using otherwise means you cannot show anything that's violation. Prove so. So you can prove that the property is satisfied, right? Just the language here. Just want you to watch out. And how do we argue logically? So here you can see there's a conjunction over here. That means in order for me to show a witness, it must be in the range. The range cannot be empty. And the property must satisfy. If either one is actually false, then this whole thing is going to be false. Then this property will be false. So now we know that this range over here is actually false because it's an empty array. So the whole thing is going to be false. So that's why we return false. I'll write it down. So here, for empty array, as we said before, R of I is false always. In that way, we got also something called zero of conjunction. False and anything is simply equivalent to false, right? So you definitely want to link what we're trying to say here to what we said last time. Over here and also over here, all right? Any question so far? Okay, it sounds like, seems like it's clear. All right, so let's now move back to the slides. Sorry. Okay, so here in predicates, we definitely have to use variables. You can see it's a plural. You may have to use more than one variable. We'll definitely see example many times. And there should be a universal disclosure, so that should be a range of variables. Range of values, like a type for the variables. And we use the following symbol for common numerical range. Oh, so this is important. Okay, I'll write it down here. These two symbols are really important. Okay. So here, this is how you write it on the paper, something like that. So this is the set of all natural number, going from 0, 1, 2, and etc., all the way to plus infinity, conceptually. And notice that it includes 0. I heard that in some other course or textbook definition, they sometimes don't include the value of 0. For this course, we do include 0. I want to make it clear. Okay? The other symbol you want to know is this. It's like a Z and put something like this. Okay? That will be the set of all integer numbers. And that'll be minus infinity all the way to 0 and all the way to plus infinity. Right? Simple definition. And of course, you can see 0 is also included. We're going to talk about, hopefully, some basic set operations, right? Do you guys remember this symbol over here? Right? Subset, right? And also this, what about this? Do you remember the term for that? It's it's a special term for that. Proper subset, thank you. Yeah, we're going to review the definition very soon. Okay, so after we have gone through the definition, I do have some exercise for you. I've got to write it down, and you can check. Very easy to check. You want to check to see? Let's say over here. Okay, exercises, you can easily check. You can check to see natural number, like that. Symmetrically, you can also check integer, a subset of natural number. Okay, I'll do one more. How about this? Natural number, proper subset of integer. And also integer, proper subset of natural number. Okay? Should be quite obvious. Okay? But it's an exercise for you. If you're not too sure about the answer, you don't think it's straightforward to you, drop by my office hour. We'll talk about it. Okay? Okay, let's go back to the slides. And variables may be quantified. Well, we'll talk about universal and also existential quantification. You just got to remember, whenever we talk about universal, we want to check all the values should be satisfied in that universal disclosure. Whereas for the existential quantification, there should be at least one. Okay? So far we talked about kind of informal meaning. Of course, we gave some formal syntax about the two quantification. What's really important for you guys to know is to say, I give you some predicates, like a quantified expression, use either operator. How can you prove the predicate either being true or false? There should be some strategy for doing that. Well, we'll get there, right? It will come. Okay, predicate logic, and then universal quantification. Okay, that's a syntax. We spoke about it already. And just notice that x over here is a comma-separated variable. So for example, let me just put it here, just in case. Yeah. One example would be, oh, wrong way. There we go. You can say something like, for every, maybe I, j, right? Comma separated, and you can say maybe I is a natural number, and j is maybe an integer, and then if they're in the range, then there should be some property of I and j that should be satisfied, right? I just want to show to you, if you got more than one dummy variables, you want to put a comma to separate them. You might see that quite often. And the same goes for existential quantification. And maybe once you have, let me also highlight. In lab number 1, you want to pay attention to how to write quantification in Rodin. They have some special syntax for that, okay? Pay attention to how for all n exists should be written in Rodin. Okay, I'll let you pay attention to it. It's already on the lab 1 material. All right. And okay, so that's the syntax where we talk about. And the idea will be for all the, let's see here. Let's see. If you only got a single variable here, so you're basically saying for all the possible value I, such that it satisfies this range, it should be the case that the property is satisfied, right? If you got multiple variables over here, the same idea. You want to say for all the possible combinations of I and j, such that I is a natural number and j is an integer value. In that case, this property should be satisfied. That's why you saw the combination word in the slides, right? You want to make sure you consider all the combinations. We do have some example coming soon, okay? So what you want to notice is this particular implication should really hold for all combinations of I and j. Of course, you may also have 3 or 4 or 5 different variables separated by comma. All right, let's now do some quick exercise. Okay, I believe I do have that over here. All right, guys, just tell me true or false. Okay, the first one. Oh, let's do one thing at a time. Right? Don't go too far. Don't go too fast. This one. True. Okay, basically, think about if you want to show, kind of see if a universal property will be true. Try to think about all the possible members. For I being natural number, the smallest one would be 0, right? 0, and then 1, and then 2, and etc. Of course, all of them larger than 0. That's easy. Okay? What about the second one? False. Okay, very good. That one there, how do you show that it's false? Yeah, exactly. So what Adeline just said is more like a proof strategy already. But let me write it down informally. Because we know that this is going to -2, for example, is a member of this particular integer, right? So it's going to be false. It's not the case that all the integers are larger than or equal to 0. Very good. Intuitive. Guys, how about this? False, okay. So you can see here, we got I and j. So we got to consider all the combinations of I and j. So can you give me one combination of I and j that's going to fail? This one here. I equals j, very good. This one here, for example, when I is equal to j. let's say 3 and 3. So now if you try to evaluate 3 and 3 here, 3 is an integer and 3 is an integer. In that case, you're going to get true over here. 3 less than 3, false. 3 larger than 3, also false. And false or false is going to be false. So true implies false is going to be false. That's how you justify, right? I'll try to write it down a bit, just in case you're still following the details. So here, let's say we do 3 and 3, right? So 3 being an integer and 3 being also an integer. This whole thing over here is going to be true. And over here, so 3 less than 3 or 3 less than 3. That's going to be false. And then if you have true implies false, it's going to give you false. Okay, very good. Okay. And what about this one here? The first one, existential. True, as long as you can find a witness. Give me a witness. 1, 0, right? As long as it's actually in this range and it's larger than or equal to 0. So this will be also true. For example, I can give you a witness 0 or 1 and etc. How about this one? True, right? If you compare what we had before, this one here and this one here, right? By changing the quantification, we go from false to true. Because here it requires every member in the universe of disclosure. Here just requires just 1. Okay? So that's also true. For example, let's say just 0. Right? Okay, one more. How about the final one? True? If you think that's true, give me a witness. How about 3 and 4? Okay. How about I being 3 and J being 4? In that case, what's going to happen? This part over here, okay, let me just write it down completely. For this part over here, right? This part over here, 3 is an integer, and 4 is an integer. True. Agree? That's the left conjunct. What about the right conjunct over here? Here, remember we got disjunction, not the conjunction here, right? So in that way, 3 less than 4, or 3 larger than 4. You basically got true or false. You still got true, right? All right, so you got true over here. So you really got true and true. So true, right? So this will be the witness, right? Very good. Overall, it's true. Okay. Any questions so far? These are simple. I think when it gets a little bit closer to your written test number 1, I'll give you something slightly more challenging, slightly more. Okay. Okay, having warm up about how we can decide whether or not the universal existential quantification should be true or false, let's now get a little bit more formal. It's more about proof strategy. Okay? And I'll be talking about all the examples here, 3 here and 3 in the next slide. I'll talk about them already. But let's now talk about proof strategy for both quantification. Okay? And let me present them at one go so we can compare them. Okay, first of all, let's understand what we are trying to do here. For any given universal quantification, you may either want to prove it or disprove it. For any given existential quantification, you may either want to prove it or disprove it. Well, we're considering all the possibilities. Let's do that, the strategy abstractly without any concrete example, but we'll talk about concrete example. Next one. Okay. Good. I'll give you a little bit hints over here, okay? So you can actually follow the logic that's laid out in the slide quite easily. You basically want to think about if you want to prove universal quantification, you somehow want to find some false value for implication. In order to Oh, sorry, let me say it again. Pardon. If you want to prove a universal quantification, you want to find how can I make this implication true to prove it, right? Symmetrically, if I want to disprove this universal quantification, I want to see how I can make this implication false, right? To really prove, you want to show true. To really disprove, you want to show false. Okay, let's do these two first. Okay, prove this and also disprove this. Let's talk about these two, right? Any insight you want to give to me? Is there only one way to prove that the universal quantification is true? Or there are more than one ways to prove it, given that it's an implication? And of course, in order to really answer this question, I assume you know the truth table of implication pretty well. If you know, you want to catch up, all right? So everything is connected. That's my point. Anybody want to contribute? You.
My point is that maybe we can prove that every I for the P is not satisfied and every I for the R is not satisfied.
Sorry, say it again. I don't quite follow you. So prove this, right? How do you prove it? Yes.
If P is not satisfied, then R is not satisfied.
You're saying P is not satisfied,
Yeah.
and also R is not satisfied. Yeah, basically you're talking about false implies false, right? But I think the way you say that is not general enough. But you do mention one case. One way to prove that this implication is true is if we can just show that the universe of disclosure is simply empty, right? Remember what you said before a few minutes ago? If the universe of disclosure is simply empty, the universal quantification is trivially true. That's one way to prove it, if you can show it, okay? So approach number one. Show that Ri is always not the case. I put a negation there. And if you want some intuitive explanation, i.e. empty universe of disclosure. Right? And also, you want to remember the zero of implication, which would be false implies any P is equivalent to just true. Right? That's approach number one. Is there another approach for us to see? So you got to think about, is there other way to make implication true, other than having just antecedent being false? Is there any other way? Ryan? What do you mean direct proof?
You show that for all values of Ri will always result in...
Yes, exactly, yes. Basically, let's say the array is not empty. How do I check all the numbers are positive? Well, you show that array index 0 is positive, index 1 is positive, all the way to index a.length minus 1 is positive. You got to show all of them if it's not empty. Very good. Okay, so this second one here will be number 2. Show Ri is true and also Pi is also true. Okay, so this will be all elements in non-empty array. In that case, you want to show that every element satisfies the property. And we do have some axiom corresponding to it. Remember what we, not axiom. So just what part of the truth table. If you remember, true implies true is equivalent to true. One of the rows in the truth table, okay? Yeah, so I think you do have some nice homework, maybe before you go to bed over the weekend. So try to review what we said about propositional logic and also predicate. I'm really hoping that I can really cover up to sets. There's also one challenging concept I would like you to think it through before next class. We'll see if we can get there. Guys, any question about this? Proving universal quantification being true. Okay? It's either this or this. How about here? How do we disprove? Right? Basically, if you want to disprove this universal quantification, you want to think about how can I make this implication false? You did raise your hand. Would you like to say? Yes, go ahead. Yes, in what way? Okay, how about this? I agree with you. Yeah, let me just write it down. I like that. Let's see, let's say approach number 1. There might be more than one. Approach number 1, give a counterexample or equivalently, you can also say witness. It doesn't really matter if you say witness or counterexample. They are pretty much the same thing. Okay. Let's say I such that. What should be the property of that counterexample? Mm-hmm. Absolutely, because we know true implies false would be false. Okay, such that it's in the range, but it doesn't satisfy the property. Okay, i.e. and elements in, I'll just say array, since we talk about array, but does not satisfy the property. So one thing I want to remark a bit quickly. In order to prove universal quantification, if you're in case number 1, awesome. You should want to show that the universe of disclosure is actually empty. But 2 over here is generally tricky because you want to show for every element in that non-empty universe of disclosure satisfy the property. I just want to tell you this is a trickier case. Right? Of course, depends on the case you're dealing with. This one here is a tricky one. I'll just say harder one. And for this one here, not too bad. You just want to give a single witness to disprove. Just remember this pattern. And we'll see that, interestingly, for existential quantification, it will be the opposite way. Okay, let's see. Okay, hopefully everybody's still comfortable, right? I just want to make everything, flow, right? How about proving some existential quantification where we actually got conjunction, meaning that it should be in the range and it should satisfy the property. How do we prove it? Yeah, exactly. So I would say this one over here, to prove existential and to disprove universal, they're similar. Not the same, but similar. Okay, similar. But let me write it down precisely. So what you're going to do is only one approach. Show a witness. However, when you want to show that an example that actually satisfies the property, you wouldn't call that a counterexample. Usually we only say counterexample if that particular witness is used to show the property is not satisfied. But if you use the witness to show that some property is satisfied, in this case, we wouldn't call it a counterexample, right? You can see, right? So show a witness I such that over here, it should be in the range, and also it should be satisfying the property, right? You can definitely see PI versus not PI, right? Just notice that. They are not the same, but similar. All right? That's the only way. You can think about to really make this conjunction true. The only way to prove it true is when this is true and this is true. Finally, how do we disprove? Is there more than one way or just one way? How can we make a conjunction false? Why don't you mention one way, please? Okay, go ahead. Yeah. For disproving, yes, the final one.
So we basically use strategy number 2 for the first one.
Yes?
So we just show that for all I, right?
Okay.
Oh yeah, show that for all I.
For all I, yes, in some way, yes, but that's a little bit indirect. How should I write over here a proof strategy? We want to make it straightforward for you to apply. How can I show that it's false? Basically, think about if you got a conjunction over here, you can either show that this is false, or you can show that this is false, right? So to show this is false is basically this one here, empty collection, right? That's the example we just did in the beginning, right? That one, let me write it down. Number one, show not Ri. So empty. And if you remember, if you got not I or not R, so false and P will just be equivalent to just false. That's the zero of conjunction, right? Is there another way to show that, to disprove it? I'm pretty sure you know the answer, but let's see if there's anybody. Guys, is there another way to show that this conjunction is false? One way is to show Ri is actually false. Is there another way?
Would it be to show that Ri is satisfied, that there's no PI that's satisfied?
Absolutely. That's spot on. Exactly. Guys, I'm pretty sure you know, but just don't be shy. You can sometimes shout it out. What you really believe is intuitive, you might just be right. Very good. Show. Oh, okay. So you know what? Here. Show a witness I such that it will satisfy the range, but it does not satisfy the property. For both of them, I forgot to mention one thing. For both of them, right, there should be something I forgot to mention. Show some counterexample, of course. Show some counterexample, and also, or you can think about it's a witness. Okay, so now, a similar remark. We said in the case of the universal quantification, this will be the harder one because you got to consider every member in the non-empty universal disclosure. What about existential? Which one will be the harder one? It turns out this might be the harder one, right? This one is to say, given that the collection is not empty, I want to show that every member in there does not satisfy the property, so that I cannot show you anything that's satisfying, right? So that's a harder one, all right? So this one over here is the harder one. It's very interesting. Now, in order to show that universal quantification is true for some non-empty collection, that's a harder case. To show that the existential quantification is false for certain non-empty collection is harder case. Right? Think about what I just said. Think about it. Okay? Right? That's a proof strategy. You want to make sure that's clear to you. Okay? And we have done with all the slides over here. You can definitely look at them. They are exactly what I just mentioned to you. Okay? So what we should do now, before we take a little short break, is why don't we do one more exercise, okay, to why it's still fresh in your mind? Yes, of course. Ed, and then go ahead. What question do you have? Oh, sorry. He's absolutely right. So I do say something that's not exactly precise. Thank you, Edmund. That's absolutely right. So for this one here, I definitely miss. So this case number one, you want to show some counterexample such that, oh, what am I talking about? I really like it. Good. For case number one over here, you just want to show that this is empty. So there's no counterexample. Very good. Okay. And for this one here, you're right. It's not to show a particular counterexample. You want to show that for every element that's there in the non-empty universe of disclosure, the property doesn't satisfy. So there's no counterexample concept. Very good. Yeah. Thank you for correcting me. Fantastic. Why don't we do an example for each one of them? Right? That's actually on your slides. Try not to peek. All right? Let's now see how we can prove or disprove. Okay? And let's go one at a time. Oh, actually, there's no way. Okay, just only look at this one here. No. All right. Prove or disprove. Let's say this universal quantification. First of all, is it true or false? We're saying that for all the x that's integer and x is within this range, it's got to be that x is larger than 0. Right? It's true, right? So how do you prove in this case? That's a harder one. So what you got to do is you got to argue that this is how I will argue. For example, here, based on this range, I need to, it's non-empty, first of all, non-empty. And you should try to really enumerate the values if possible. So here, I'm just going to say integer, and also that should be 1, 2, 3, all the way to 10. So these are the 10 values over there. And then you can argue that every value over here is larger than 0. Right? That's how we prove it. All of them larger than 0. How about the second one? I heard false. Okay. So if you really want to prove that universal quantification is false, how would you do it? X equal 1? Okay, sure. Absolutely. So here you just want to show 1. Right? You don't really need to enumerate the range over here. You just want to give a counter example. Counter example or a witness x equal to 1. In that case, x equal to 1 is going to satisfy this range, but it's not going to satisfy greater than itself. So true implies false. So it will be false. Right? That's how you show. So when you got x equals 1, you're going to get true implies false, which will be false. That's how you show the witness. Okay, hopefully everybody's still comfortable, right? And this one. The same range, actually. But now we're basically talking about existential. True, and to really prove existential quantification true, simple. Give me a witness. 2. How about 2, or 3, or 4, whatever, right? Of course, you cannot give 1. So you wouldn't say counter example, you want to prove, give a witness to prove true. So witness would be, let's say, 2. Right? So in this case, 2 in this range, so that'll be true. And 2 larger than 1 is also true. Right? Got true and true. And that way you got true and true, which is equivalent to true. All right, a final one. False, right? Well, I kind of give you all the possible outcomes, right? But of course, in the test, I can choose any one of them. So you really have to judge to see proof or disapprove. Right? Got to be very careful. Okay? Okay, this one, you guys think that should be false? How do you argue that there's no such property, that there's no such element that satisfies property? And now, this range over here is non-empty, right? So you know that it's a harder case for existential quantification. This part over here is non-empty. So you want to argue that every element there is going to falsify the property. So non-empty range. Non-empty range, so you got 1, 2, 3, all the way to 10. And you can see all of them makes x larger than 10 false. That's one way to write it. Of course, you got to write a little bit better. I'm just trying to sketch the idea quickly. You can see the more, like a better writing maybe on the slides, right? But you do get the idea. Any case that kind of still bother you, that's not clear. Adnan, please.
I know that these ranges are very small.
Mm-hmm. Yes.
The range was very large.
Yes, very good question. So I think even for small range over here, you can see I didn't really write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I didn't write it, right? I kind of used ... to say, as long as the pattern over here is very clear, and the way you actually make a conclusion to say all of them satisfy certain properties convincing, that'll be okay. I'm not sure this can be imagined right now. If the range is really big, right? Sometimes you may have to say, okay, these are all the values in that particular range. Maybe I can discuss for case number 1, for case number 2, and for case number 3. For each case, it's actually going to satisfy the property. That's another way to argue. Yeah.
We also use some sort of
Induction, we don't really need like a mathematical induction, not really for this course. We may need to maybe make some analogy to mathematical induction, maybe later. But for proof, you don't really need it. If you really need it, I'll make sure I review and let you know beforehand. Okay. Yeah. Yes? Say it again. Which one do you want to say? The first one. Okay. What do you want to say? No, you have to argue that for each element here, you're kind of mixing different ideas over here. When you say the range over here is larger than 1, you cannot say a range is larger than 1. You can only say the size of the range is larger than 1 or so. So here you want to say is, this is the enumeration of the entire range, and then you want to say every element over there is larger than 0. That's how you should say it. There's no other way.
Can I say the lower bound of this?
Of course, in that case, you have to make it very explicit to say, okay, we're starting from this, maybe arithmetic sequence, and where the lowest number is already larger than 0. Of course, everything will be larger than 0. That may be another way to put it. Of course, we'll judge. Yeah? The idea will be you have to somehow cover for all the elements in this particular range. You want to mention them, each one of them, and then they should all satisfy this property. That's the bottom line. Yeah. Okay. All right, I think I just got, let me just double check. I got one more property. Yep, just one more property. Why don't we do this after the break? Let's say we take attendance now, and we can take a short break. And then one more example, one more property, and then we can move on to sets. Okay, I already updated my location, so you guys can just check in right away. Let me start the class. Okay. And then, excuse me, I'm going to say poll. Okay, you can check in. Okay, any issues? So guys, please do it now. All right? If any issue, come right to the front, please. Right to the front. All right? Any other issue? Are we okay? Okay, I'm going to close the poll. All right? So, at the same time, why don't we take a 3-minute break? Please don't go too far, 3 minutes. Okay, if you got an issue, come to the front. Doesn't work for you?
I couldn't find the course I had it last time.
Oh, yeah, you want to set it up? Okay, maybe set it up next time. Okay?
I did have it before, too.
Uh-huh.
Can you go back to the note?
Let me deal with your classmate first, and then I'll talk to you. Okay?
Just take the note.
Take the notes?
Yeah.
Oh, that's what you want?
Yeah.
Okay, sure. Give me a moment. Which one?
The one that showed the methanol to.
This one here?
Yeah.
It's allowing me to join now.
Yeah, so once I close, I don't want to reopen. So why don't you, do you have a pen yourself?
I have a pen.
Yes. Why don't you find your name over here? Are you enrolled already?
Yeah.
Okay, yeah, find your name and then put a check mark and then sign. Okay?
Okay.
But next time, start earlier. Okay? Yeah, okay. You as well, right?
Yes.
Okay, yeah.
It was just blank.
Okay.
It didn't show me anything.
Just fail.
Yeah, sorted by last name. Yeah. Awesome. Yeah, put your name, signature here. Thank you. Awesome. Same issue for you or question? Yeah, go ahead. Let's take a look at maybe briefly after class.
Okay.
How about that?
Yeah.
Thank you. Good man. Mm-hmm.
I'm trying to say that.
Right, it's going to be brief. Otherwise, we're going to resume very soon.
It's like, because I just want to say, if we use like s larger than 1, larger or equal than 1, and then smaller than 10 as a set,
No, you cannot say that.
as the definition of the set.
No, you can. Okay, why don't you tell me exactly what you thought? Maybe after class. I need to think about it.
Yeah, because I think I need to write. So
Yeah,
this-
I need to see that precisely. Otherwise, I might just give you the wrong answer. Yeah. All right, guys, just 1 more minute. All right. All right, just 1 more moment. We should really get started again. All right, let's resume, shall we? All right, so the last example or property I want to show is how you can convert between universal and existential quantification. I'm pretty sure you have seen that in 1090. So what I want to do is, I can make two things I can do together with you. Number one, we can try to understand these two conversions intuitively by using some example. I'll talk about it, okay? Number two is, I can show you very briefly how this is supposed to be derived. That's also something I can show. Why don't we try with the intuition, okay? I wouldn't write it down, I'll just say that, but of course, it's easy for you to write down later. Let's say the universe of disclosure is about the 3342 class. So we say a person X is in this universe of disclosure. So a student like you guys, okay? And the property is if that person in the class receives A+ in this course, okay? Let's say. How do we interpret this? Of course, you can also try to repeat that to yourself. I'll try to say it once, and then to see if that makes sense. The left-hand side is saying this. All the students in 3342, they receive A+. What does that really mean? That means it is not the case that there exists one student in the class that does not receive A+. Make sense to you? If I say every student receives A+, it's basically saying there's not a single student that does not receive A+, double negation. Okay, that's intuitively what you can think. So I'm gonna save the time by not writing that down, but hopefully you get an idea, right? If you want to watch the recording, you can also copy down what I said. What about this one here? This one's to say there is one student in 3342 who receives A+. What does that mean? That means it is not the case that every student in the class does not receive A+. If I say there's at least one student who receives A+, I'm saying that it's not the case that nobody receives A+. Hopefully that makes sense to you, right? So you can really try to plug in these two, this range constraint and also this property by different stuff to really convince you. Like these two are really the way to convert between the two. Either to go from universal to double negated existential, or you can go from existential to double negated universal. Okay, intuitively. Are we okay so far? Just about intuition. Now, what about logic? If you really don't like intuition, want a logic, right? Thinking this way. You may have to use a little bit De Morgan, okay? If I start from this, okay, let's say I start from this. The idea would be we want to have the double negated, right? We want to say not the case. There exists X such that negate the property the whole implication. Rx implies Px. Okay, let me just make sure I got it right. Okay, so what did I do? For all to exist, and I say not the case exists, and then I negate the entire implication. Okay? And do you guys remember the definition for implication? Not P or Q. Remember? Okay? So then we could put this negation still here. There exists X, negated, and then R, not P or Q, sorry. not P or Q. So you can think about, I basically go from here to over here, right? Implication has been transferred into not P or Q. That's what I did, all right? And De Morgan. This would be equivalent to, if we do De Morgan, and also double negation, right? If I got not the case, some disjunction, it would be, well, if you have to remind you, not the case, P or Q, equivalent to not P and not Q, right? That's also one of the theorems we had, okay? Let's try that. So we still have this. There exists X, okay? So now, what can we write over here? Okay, so not. So we just got Rx and not Px. And isn't that just the same? That's how you prove it. Nice property here to see the proof. You need to use definition of implication. You want to use double negation. You want to use De Morgan. We all mentioned that, right? They are basic ones. How about this one here? How about exercise? Okay. If you want to show me your proof during office hour, you're welcome to. You'll follow the same idea. Any question here? Right, so we did two very quick review for you to really see the conversion between from here to here or vice versa. You can either substitute the range and the property by something you feel comfortable with and try to repeat yourself what that really means, right? Like what I did, and it should make sense. Second thing is you can look at how we can rewrite what's really inside by using the properties we review about proposition, and then you can get this too. Okay, whichever way you like. Okay. That's about predicate logic. Do we have any question before I move on to sets? Anyone? Good. Okay, so what I want to do now is to move on to sets. I got about 17 minutes. What I would suggest, I will go over some basic definition. I do have some intermediate basic exercise. I'll skip that today. That one there, I'll let you look at that over the weekend. We can go over answer very quickly next time. I really want to talk about the power set idea. I really want you to struggle through that a little bit over the weekend, because when we start defining relation and function, you have to use power set all the time, right? That's my plan. I really want you to think about something harder over the weekend. Okay, let's now take a look. Okay, we already talked about it before the break, and that's about the theorems, right? The conversion we just talked about. Set. Let me go over the definition quickly. A set is simply a collection of objects. Here, object, by the way, is not Java objects. Any objects can be a set of chairs, a set of TVs, a set of iPads, and etc. Not really Java objects. It's not that restrictive. Very general. And they are called elements or members. I believe members might be the more formal term, but you can say element, that's okay too. And the order in which the elements are arranged does not really matter. So, for example, let me do this. Give me a moment. If you write a set, for example, 1, 2, and 3, it's the same as if you say 2, 3, and 1. The same. The order doesn't matter. And elements can appear at most once in the set. So you wouldn't write a set like this. 1, 2, 3, maybe 2. Right? You can see it's repeated. That's not something you will write. They should appear at most once. Okay? Also easy. And we may define a set using, okay, set numeration. Okay, that one there is just about enumerating all the elements in the set over here. 1 and 2 and 3. Another way to do it would be the so-called set comprehension, right? So set comprehension, I forgot if I really mentioned that in the lab number 1. I forgot, I can check. If no, I'll try to give you more example. But set comprehension will be something you have to deal with more, okay? Let's look at one example right away, okay? So here is a syntax. Set comprehension. Okay. Basically, oh, sorry. The curly brackets, and then you have some vertical bar over here, okay? So this part over here will be a list of variables. And this part here is a single predicate constraint. As long as the variables over here satisfy the constraint over here, that element should be included in the set. That's the definition. For example, if I say the set of, let's say, x such that x is a natural number, and let's say x larger than 5. So here, it's a way to actually represent a collection of elements or objects, right? So here, what should that be? It should be, well, it's not the set of natural number anymore because you also need to satisfy this. In that way, it should be starting from 6, right? So it will be like a 6 and 7 and 8, all the way to maybe infinity, conceptually, okay? But you'll see more example on the slides, right? So comprehension, we'll definitely revisit this with more example. For now, I just want to explain to you the syntax. Okay, empty set, you can write it either as, so empty set, either like this, or you can say this. Either way. In Rodin, you have to type in ASCII this, and then it will be visualized as this. Okay, you'll see that in Rodin. And we may check if an element is a member of a set, right? That's a membership symbol. So you might say something like, for membership, you might say 5 is a member of natural number. You might say -2 is not a member of natural number. Pretty easy, right? Okay. I do have some exercises on this basic construct, but let's do it next time, okay? But I do really want to talk about power set. Cardinality, right? Easy. So cardinality, just put like an absolute value. So we'll say the cardinality of the empty set is simply 0. The cardinality of, let's say, 1, 2, and 3 is, in this case, 3. Of course, the set over here, you can also put some set comprehension expression, and you got to figure out what's the precise size. Okay? Okay, set relations. We talk about subset, right? There's a subset symbol. You want to say if, I say S1 is, let me visualize that, right? You can look at the predicate a little bit, and then I'll try to go over the predicate a little bit more carefully next time. But let me just do that here. You can visualize very quickly here. If I say S1 is a subset of S2, in this case, you can think about, we might got S1 over here, and we got S2 over here. And this part over here is so-called the difference between the set. S1, set minus S2. Any element that's in S1, but not in S2. Oh, I beg your pardon. This one here, let me see it again. That would be S2, set minus S1, okay? In S2, but not in S1. In the case where it's a subset relationship over here, then this set difference over here may be empty. Maybe or maybe not. Okay, there's another relation here. If I say S1 is a proper subset, right? In that case, you can definitely visualize this. Again, S1, proper subset of S2. And here, S2, subset difference S1, must be non-empty. There's got to be one element over here that belongs to S2, but it's not in S1. That's why it's a proper subset, right? So guys, take a look at the definition on the slides, right? So that's rather easy. Okay. And I will do the exercise, I promise. I'll do it together with you on Tuesday. You can take a look. And we'll talk about union, intersection, difference, and power set. Let's do this. I got 9 minutes. Okay. If you don't mind, I'll take 10. Okay, let's see. Power set, very important. The power set, by definition, we're going to use this notation to show to you. Oh, sorry, my computer freezes a little bit. Okay, that's a definition. Okay, let me show to you. If I'm having a set, the power set of S, by definition, is going to be all the element X such that X over here is a subset of S. That's a funny definition because, okay, one thing you must note. Each member in a power set is a subset. Very important to remember. It's a subset, which is a set, of course. It's a set of sets, basically. And let's do this example right away. And I will show you a very systematic way to calculate it. And then we want to generalize it. That's what I want to finish today. Okay? Overall, if you want to compute a power set of 1, 2, 3, well, of course, you can also write it like this. Power set of 1, 2, and 3. Let's try, this is what I want to do. I want to enumerate all the elements in the power set, and then we want to generalize how we compare the quantity. Like how many subsets are really in a power set. Sometimes I may give you a question where I don't ask you the contents of the power set. That's why I'm talking about this, okay? So let's enumerate first. It's going to be a very big set, like that. Each member there is going to be a subset. Let's try to be systematic. What will be the smallest subset a set can contain? Empty set. Very good. Cardinality is 0. I'll put a comment here. Cardinality is 0. Thank you. Oh, by the way, this does not belong to it. I'm just showing you some comments, right? What will be the largest subset? The set itself. Very good, guys. Pretty good. Thank you. So this will be 1, 2, and 3. This will be the final one. So that'll be cardinality 3, but I want to be more precise. Cardinality of the set itself. And you can see, so that means how many more categories should we still need? We got cardinality 0 to cardinality 3, still 1 and 2. We're missing 2 rows over here, all right? Let's be systematic. How many subsets are there of cardinality 1? Okay, that's easy to see. Cardinality 1. 1, 2, and 3. And here, the comma here is really important. It tells you this is a member, this is a member, this is a member, right? What about subsets of cardinality 2? How many? First of all, how many? 3, okay. I'll get to how to count this in general. Subsets of cardinality 2. So 1, 2, 2, 3, 1, 3. Isn't that fun exercise to do? Systematic. Okay, I do have about 5 or 6 minutes to make it general. Before I make it general, do you guys remember the choice operator from your math class? Here, in order for me to know how many, I can use the choose operator to say I'm going to choose one element here out of the entire set, which contains 3 elements. That will be just 3. Do you guys remember this operator? Okay, how about this? This is what I would do. I'll give you the formula just for today. I'll try to explain why it is the case next time. Okay? The choice operator is what you need. If I got n choose I, does anybody remember? If no, that's okay. Okay? N factorial divided by n minus I factorial times I factorial. I will explain to you maybe on Tuesday. It's quite a straight, intuitive way to understand, but that's okay. For now, let me make use of the time well. And for this one, over here, how many? The same. 3, of course, I know that's 3, but if you want to calculate how many, I can also use the choice operator. 3, choose 2, which will be 3. And by the way, for the choice operator, for your information, if I say n choose I, it will be the same as n choose n minus I. It's a property there. All right? But we'll get there later. Okay. So this is how you can figure basically how many there are, right? Now, what we want to do is, we want to say in general, if I give you a set S, which can be, may or may not be empty, the question is, what will be the cardinality of its power set? Basically, we want to figure out, well, empty set over here, and this one here is always just one member, right? Okay? So think about, I'll write it down here. It's going to be, if I got a cardinality of S, which can be anything, right? Now, in the case of empty set, I don't want to choose any element. It will just be 0. So this is really talking about the case of empty. Okay? And then the next one will be, what about how many subsets of size 1? That will be the size of the set, choose 1. So this will be subsets of cardinality 1 plus all the way to the final one is itself, right? So this one here is just S itself, just 1. And you guys know sigma, right? Sigma over here. Let's say cardinality C will be from 0 all the way to here. S, choose C. Do you need to memorize the formula? Maybe not, but I might just give you a question like this. You're not supposed to just use the formula and give me the final answer. I want to see the steps. So you can think about, this is This is important for you to enumerate, number 1. Number 2, you should really understand what this formula is trying to say. That will help you get some insight about the systematic derivation of the power set. Okay? And I do have 1 or 2 minutes. Let me just recap what you guys should do. So over the weekend, I would suggest you do several things. Number 1, I'm going to give you a clean page about the basic exercises. Think about these exercises and try to see if you can answer any one of them. We'll do that right in the beginning on Tuesday next week. Number 2, there is also one exercise over here at the end of the slide over here that I'd like you to do as well. Number 3, optional but highly recommended. After the power set, the next idea will be to define relations as a set of so-called tuples. What I want you to do is look at this slide here, the formal definition, and also this slide over here, the formal definition. If you can, just do 2 slides ahead of time. I can tell you, once we get a relation, the idea about power set, and also of various kinds of relational operators, it could be confusing. So I really want you to get the power set idea straight. All right? Guys, thank you so much. Don't forget, you got lab 1 to complete very soon. All right? Any trouble, let me know. Take care.